Alright guys, so the next section is about continuity. Basically the functions that we've been dealing with, we were continuous for the most part. Whenever we graphed them, we didn't really pick up our finger or our pen when we were graphing them. Even though we did have discontinuity, basically points where we had to pick up because of vertical asymptotes, right now we're going to focus on them. So first off, what is a continuous function? A continuous function is a function whose outputs vary continuously with the inputs and do not jump. And don't jump from one value to another. Without taking on the values in between. So this is just a long way of saying a continuous function is a function where if you were to start graphing it, you don't stop, you don't pick up your finger until you are completely done. So an example of a continuous functions are power functions, x squared, x cubed, x to the fourth. You can basically draw the whole entire thing without picking up your pen. Now, the continuity at a point. We're going to be starting to identify, is a graph continuous at a specific point? So the definition for this, for interior point, you are basically figuring out a function, so a f of x is continuous at C, we'll call that point C, if its domain of its domain if the limit as x approaches that point C of f of x is equal to just substituting that C in. So that's called an interior point. So that's a continuity at one point. Now the endpoint, an f of x is continuous at the left and right endpoint of its domain if for the left the limit as x approaches a from the right of f of x is f of a. So if we approach a number from the right and we just plug that in and that equals the limit, then that means that that function is continuous at a left endpoint a. Or for the right endpoint, let's call it b, as the limit x approaches b from the left, and I'll show you guys examples of this, of course, is equal to f of b. Okay? So, we have a few different types of points of discontinuity. You guys know what a removable discontinuity is. That's basically a hole. Okay? That's all I'm going to say. We know what it is. How we get it is when we cancel out factors. An infinite discontinuity is when you have a vertical asymptote. So when you see a graph doing one of these, you have an infinite discontinuity, specifically here at x equals 0. A jump discontinuity is, for example, like the step function is an example of a jump, because the reason why it's called a jump is because there is a limit, but the left and right limits are different. And then you have an oscillating. Oscillating, what that means is when you have a function, let's say it starts off normal and then all of a sudden it starts to oscillate back and forth and then it completes normal. The definition of that, it oscillates too much to have a limit as x approaches 0. So we can't really determine where it is at 0 because of the oscillation. And I'll show you a better picture of this in class of f of x. Okay, so it oscillates too much. All right, so I'm going to show you guys just a quick graph of a discontinuous piecewise function. I'm just going to draw kind of like a random looking graph. Don't worry too much about what the function of it is right now. Alright, now in this graph we can basically say that this graph is discontinuous at x equals 2, because as I was going, what happened? At 2 I had to physically pick up my finger and continue right there. And then I keep going and it's discontinuous because I had to physically pick up my finger to graph that point. So another point of discontinuity is 1, 2, 3, 4, and at x equals 4. But it's continuous at x equals 0. Okay, it's continuous. At this point I can continue on. It is continuous at x equals, sorry, I lost my count, 1, 2, 3, 4. It's continuous at 5, and it's continuous at 6. Okay, because the one-sided limit as x approaches those numbers match the value of the function. So if I was to say, what is f of 0, you can tell me that it's 2. And that matches the limit as x approaches 0. It is 2. F of 5 is 1, 2, 3, 4. Okay? And that matches the limit as it approaches 5. We're approaching 4. So we'll do more of those examples in class, of course, but this is an example of discontinuous points versus continuous points. All right. Now, continuous on an interval. Okay? A function is continuous on the interval. Let's call that interval AB, if and only if, Okay, if and only if it is continuous at every point in between. Okay, and I'll show you guys an example of that in a minute. Now, a continuous extension is basically after removing the discontinuity. So remember, like here, I'll just make up an example. So x squared minus x minus 6 over x squared plus x plus 12. Okay, remember you factor that, so you get x minus 3, x plus 2, x minus 3, x plus 4, and you're left with x plus 2, x plus 4. And of course, we had to remove x equals 3. Now, what the extension does is it allows us, let's call it g of x, is it allows us to basically keep the part that we removed somehow. So you would put the f of x function up top and you would explain what your discontinuity was. So x could not be 3. But down here, you would put that 3, or I'm sorry, not the y value of 3. And you would say that if x equals 3, you have a hole at that point. It's just a continuous extension. You're telling the reader or the mathematician that yeah, this function does have a hole at this point, but here is where that point is. That's really all it is. All right, take a minute to read this little statement, but basically what we always say is we say we have a function and we have a part that is discontinuous. So that's what we're going to do. We're never going to say that a function is discontinuous. We're going to say it's continuous, and then we're going to explain where the discontinuity is. Okay? All right, so what that means, here's the example. So show that f of x has a discontinuity at x equals 2, both graphically and using the definition. What kind of discontinuity is this? So first off, in order to graph this, x squared minus 4 over x minus 2, remember you have to simplify first. So we simplify x minus 2, x plus 2 over x minus 2. And right off the bat you see that what's left over is x plus 2, but of course we have a hole at x cannot be 2. Alright, so we see that this is the removable discontinuity. Okay, that is a removable discontinuity, aka a hole. Now, in order to graph this though, we need to figure out where the hole is. Now, I know it's at 2, but where is it at 2? Okay, so what you do to figure this out is you just basically do the limit as x approaches 2 of the function that's left over, which is x plus 2, and that's 2 plus 2, which is 4. So where is my hole? The hole is at 2, 4. So I'm going to go to 2, 4, 1, 2, 3, 4, and I'm going to draw the hole, the point of discontinuity. And then the rest of this graph, to graph it, I'm sure you guys have noticed that what's left over to graph is just x plus 2, which of course x cannot be 2, but x plus 2 is just a linear function. So we start at 2, then we go up 1, right 1, and here we go. That's all I need to be able to graph this. Done. So I've shown how I got the discontinuity. I've identified what kind of discontinuity it is. I've shown graphically the discontinuity and using the definition. Now this next example is basically a continuation, but I do need you guys to fix something. This should not be a 3, it should be a 4. Okay? So show that this has a discontinuity, both graphically and using the definition, what type of discontinuity this is. It's the exact same thing. You can tell that this part right here is the exact same thing. It's just the way that we notate it. This right here is called the continuous extension. And basically what they did is they just gave the original function and they gave the value of where the hole is. And that way you were able to fill the hole. Okay? So remember from the previous section, I'm literally just going to graph that right down here. I'm going to rewrite it. So x squared minus 4 over x minus 2. We simplify that to x minus 2, x plus 2 over x minus 2 equals x plus 2, and x cannot be 2. So when you graph this, you know that at 2, you're going to have a hole. Where is that hole? It's when x approaches 2 of x plus 2, it's 4. So by graphing it, basically what I just did, originally with this function right here, we graph with the hole present, 1, 2, 3, 4. So we graph this with the hole present. But then the second part of this piecewise function is telling me when x is 2, y is 4. So we fill the hole. And now what I just did is I turned a discontinuous function with a removable discontinuity into a continuous function. Alright? So this function right here is now g of x is the continuous extension of the original. Okay? Alright. So, filled the hole, became continuous by giving a piecewise function. Alright. Next part. Find the value of a that makes h of s continuous at x equals negative 3. So I want to figure out, basically, all I'm figuring out right now is what is the y value of this hole. That's what a is. Okay? A is what's the y value of the hole at x equals negative 3. So in order to do that, step 1, we're going to factor, reduce the top function. So x squared minus 9 over x plus 3 equals x minus 3, x plus 3 over x plus 3. So right off, you see that this cancels out. So what we're left with is x minus 3, and of course x cannot be negative 3. So here's my function that I'm actually going to graph, but this is also the function I'm going to use to find my a. So step 2, use the remaining simplified function to find the limit as x approaches 3. So, and the reason why, I'm sorry, it's negative 3, sorry. The reason why it's negative 3, first of all, it says it up here. We figured out that's our whole, so we got to use it here. So as x approaches negative 3 of x minus 3 is negative 3 minus 3, which is negative 6. So now I know two things. This is the y value of my removable discontinuity. I know I've spelled discontinuity like 100 different ways, but it's okay. And that is my A. Alright, so A equals negative 6. So now when I graph this original guy, 1, 2, 3, 1, 2, 3, at negative 3, negative 6, I would have had a hole. And then you graph negative 3, then up 1, right 1. So if I was just graphing this top portion right there, this is how my function would look like because it has a hole. But because I am graphing this along with the extension, which is now negative 6 when x equals negative 3. So at negative 3, at negative 6, I'm going to fill the hole. Now it becomes a continuous problem using the continuous extension. So pretty easy. Okay, a lot of it is old stuff that we already know. Normally we would have just plugged in x. Now we're using limits to find the y. Before that, we didn't do this. We just basically took the negative 3 and plugged it in directly right there. Alright, just got to plug in my computer. Give me a sec. Alright, and then the last section, discuss the function f of x equals 1 over x in terms of continuity. Now, right away you know at the exact point x equals 0, what happens to the function? So at x equals 0 is a point of discontinuity because f of x is undefined. That's pretty straightforward. Nothing new. Alright, so before I move on, I want to graph this function 1 over x. And then this next part, you'll see why I'm graphing it in just a second. This next part, I basically want to ask myself, is the function continuous between this interval, between 2 and 5, and between negative 6 and negative 3, and between negative 3 and 2? Is it continuous? So first I'm going to graph. Alright, I know that at 0 there's a vertical asymptote. I'm going to try to be as accurate as possible. At 1, it's 1. At 2 is 1/2. Okay. At 4 is a quarter. So we see that the graph kind of does one of these. And then of course the other way at negative 1 we're at negative 1. At negative 2 we're at negative 1/2. So the graph does one of these. Sorry. Alright, so now the question is between 2 and 5. is the graph continuous? So I'm going to look at between 2 and 5. Is it continuous? Do I pick up my fingers at all in between those two functions? Absolutely not. So between 2 and 5, the graph is continuous. Now between negative 6, 1, 2, 3, 4, 5, 6. So between negative 6 and negative 3, is the graph continuous? Do I pick up my finger at all in this little interval right here? No, the graph is continuous. But between negative 3 and negative 2, negative 3 and 2, so between this point and this point, is the graph continuous? Absolutely not, because I physically have to pick up my pen and start up here again because of this vertical asymptote. So it's not continuous. And what kind of discontinuity is it? Because of the infinite discontinuity at x equals 0. So everywhere is this continuous? No, it's not. And I'll elaborate on this a little bit more. So basically we know that a continuous function is one that is continuous at every point of its domain, which means the x values, okay? So that's for a continuous function. But of course you can have continuous intervals, and we'll talk about that tomorrow. Alright, so part 1 done. We'll finish up part 2 another time.